Welcome to the course of conformal field theory. We'll also call this thing as CFTs, stands for conformal field theory. We'll just abbreviate it with CFT. And this video will be really just an introduction to conformal field theory. And I'll just introduce you to the subject of CFTs, and we'll discuss in this video some of its applications and uses and why should one be studying conformal field theory. And by the end of the video, I'll also be giving you some of the references, more or less some of the books that you can follow to study conformal field theory yourself. And those would be also the references that I'll be following along for the upcoming lectures on conformal field theory. So first, let's just get this out of the way, that what is conformal field theory. Of course, I cannot explain you everything in this one video, and so that's the goal of this series or playlist, that we want to understand what is conformal field theory, and then we'll see also some of its applications in the upcoming videos, right? But let's just give a general statement of what is quantum field theory, so you have an idea what we'll be studying in this course of CFTs. So really, a conformal field theory is just a quantum field theory, really, and it is a type of a quantum field theory which is invariant under conformal transformations, right? So I'll just write CT for conformal transformations. Now, of course, there is a question that what is then conformal transformations, right? And we'll, of course, be discussing this as well as we progress forward in this series. But again, a very general thing that you can think of this conformal transformation as a change in x coordinate, or any coordinate for that matter, and this coordinate changes to some x prime, and what this does in turn is it changes the metric tensor in a very particular way, right? So g goes to g prime, really g mu nu goes to g mu nu prime, right? And it is done so in that way that it remains invariant up to a phase of g mu nu, which is a function of x, which is really this coordinate that we talked about, and it transforms to some g prime mu nu, which is a function of x prime now, because x has transformed from some x to x prime, and this new metric tensor is just a product of this transformation lambda of x times g mu nu of x, right? And what happens is, after this conformal transformation, you will be left with a new coordinates, so that's x prime, and you will be left with a new metric tensor, which is this g mu nu prime. All right, so we'll just keep it simple up until this point. Now let's also talk about why should you study conformal field theories at all, right? So that's another question. So, well, there are many reasons. One of a very basic reason is that conformal field theory is at a frontier in physics, right? So it's at the frontiers of theoretical physics. And there is lots and lots and lots of research that is still being done on conformal field theories. So you can still find some very latest available research papers related to conformal field theories. As again, it's not completed really at this point, and so there is some ongoing research in this field. Now, what is more is that these techniques that you will see that we'll be developing in conformal field theory, these techniques are extremely useful in what is known as string theory, right? So techniques of conformal field theory are applicable, or in fact, you cannot do really string theory without having some knowledge of conformal field theories, right? So they are applicable to string theory. So these techniques that we'll be developing in conformal field theory, they are going to be used in further. I'll also try to cover this topic of string theory, right, in one of the future playlists. And these techniques that we'll be developing over here are going to be useful for you if you're going to if you have any plans for studying string theory as well. Now, how is that the case, right? You might ask, well, how is that? Why am I saying that these techniques are useful in string theory? What is the relation between conformal field theory and string theory? I'll just short string theory with ST, right? So that's string theory. I'll just write it over here as well, right? So what relates these two things? Well, we'll see that in future videos as well, but a very shorthand description or a rough description you can think of is that really that the string theory is is almost the two-dimensional version of a conformal field theory, right? So string theory in that sense is really a conformal field theory whose degrees of freedom are limited, right? So two dimensions, conformal field theory. And once you do a two-dimensional conformal field theory, this thing leads to gravity as well. So gravity just pops out of two-dimensional conformal field theory, which is string theory, and hence you can say that a building up from conformal field theory to string theory is important in that sense, or many people are fascinated by string theory because of this thing, that gravity, you don't have to insert gravity into string theory. In fact, what happens is that gravity just pops out of string theory itself, right, which is a two-dimensional conformal field theory. Moreover, another use of conformal field theory is in condensed matter physics, right? Condensed matter physics also uses conformal field theory in multiple ways, and one of the ways is that in CMP you have something called phase transitions, right? And these phase transitions can be studied using the techniques of conformal field theories. Another way of saying the same thing is that CFTs will describe systems. CFTs will describe systems which are, you can say, describe systems near criticality. So this criticality is, you can think of it as, the term comes from the fact that we have when you have a phase diagram, right, in condensed matter physics, for any particular material you will have some phase diagrams, and those this criticality is really also known as a critical point, really a quantum critical point, and it is that point in that phase diagram where you will see a continuous transition of phase happening at the temperature of absolute zero. Right. So now we have already mentioned that this thing CFTs are really quantum field theories, right? In a way, and let's see. When you study quantum field theories, how is CFT different from quantum field theories? What is the advantage of a conformal field theory when compared to a regular normal quantum field theory that you study? Now, if you have studied quantum field theories, you know that in quantum field theory there is something known as a cutoff point. Now, of course, I'm not going to go into the details of cutoff, but cutoffs are just a number. It's a number for energies, for example. It is a maximum or it could be a minimum number or value for energy where if I have any system which has energies lower than that cutoff or higher than that cutoff, then those energies can be ignored in some particular computations, right? Now, the beauty of CFTs is that it is independent of these cutoffs, right? So it does not depend or have these cutoff momentum or energies in a conformal field theory. And that's why some people will also say that the conformal field theory is the only true quantum field theory, right? Because you don't have to deal with those cutoff points in a conformal field theory. Moreover, conformal field theory is it is very rigorous when compared to quantum field theory, right? And the reason for that is that quantum field theory is developed using the Feynman's path integral approach, while CFT is very mathematically rigorous in its calculation, right? All right, so well, that's some of the basics of conformal field theories, right? Now let's end this video with some of the references to conformal field theory. So I'll list down some of the references that I'll also be using in the upcoming videos that will be made on conformal field theory. And these are some of the references that you can also go to learn conformal field theory yourself. Well, first I'll list a reference which is really a paper, right? It's a paper by Ginsberg, and the name of the paper is Applied Conformal Field Theory, right? Applied CFTs. Now, this paper was published in 1998, right? And this it is not a small paper, it's a very large paper, and it covers lots of topics in conformal field theory and its applications as well, right? Now, the other reference that I'd like to point over here, which is something that I'll also be following along quite often, right? In fact, in all of these videos, more or less, I'll be following this particular book that I'm going to list right now, and it's Introduction to Conformal Field Theories with applications to string theory, right? So this book is written keeping in mind that they are going to give you a basic introduction to conformal field theory so that you can build up on your concepts of conformal field theories, and then you can use that to in applying it in the study of string theory as well, right? And these are really lecture notes and lecture notes in physics, and the author of this book is it's Blumenhagen, right? Blumenhagen, right? So in this book we'll be covering lots of topics, right? The most important topic of this book is the second chapter, and that chapter is basics in conformal field theory, right? And in this topic, you'll cover things like the conformal group, where we'll talk about conformal generators and the conformal algebra as well. You talk about a lot of things in this chapter, right? So we'll talk about conformal groups, conformal algebra. We'll talk about conformal groups in different dimensions, the energy momentum tensor. So of course, I'll not list everything, but let me just write down some of the things that are important from this chapter. This chapter itself, the second chapter, Basics in CFT, is really important. So you'll be also talking about the Hilbert space of conformal field theories, Hilbert space, right? And we'll discuss some of the examples of conformal field theories, right? Conformal transformations. We'll talk about the bosons, free bosons, and free fermions, right? Bosons and fermions in terms of CFTs, and a lot of things, right? And then in this book there are further chapters which talks about and now I'm not going to list all of that over here, but I'll just dictate it. We'll talk about symmetries of conformal field theories, where in this book you can find different topics of Kac-Moody algebras. You can find the coset construction of those. We'll talk about some of the algebras. Then further, the book also talks about a conformal field theory on a particular geometry, which is of a torus, where you'll look at different partition functions. We'll develop a partition function, and then we'll look at multiple examples of those partition functions for a boson on different types of geometries, right? We'll talk about boson on a circle. We'll talk about boson on orbifolds, and so on, right? And then we have in this book, you'll also see super symmetric conformal field theory, right? And that is another very big topic of conformal field theory. You can find some of the topics from supersymmetric conformal field theory, where you'll talk about superconformal models, different types of superconformal models. We'll talk about then coset constructions of these conformal models as well, and a lot of other things. Finally, there is one very important topic of this book as well, which is if you're concerned with the boundary conformal field theory, right? So the topic is, I think it's called the boundary conformal field theory. It is, if I recall correctly, it's the sixth chapter of the book, and it's known as boundary conformal field theory, right? And in boundary conformal field theory, you'll talk about again bosons, but with boundaries this time. We'll talk about the boundary conditions for that free boson, and then how does the partition function changes with these boundary conditions. We'll talk about the boundary states and a lot of other things as well. So more or less that's it for this video. It was just an introduction to conformal field theories. We did not do a lot of mathematics or anything. Of course, in the next video, we'll be doing lots and lots of mathematics. So if you need to brush up on your tensors, right, tensor calculus, it would be very helpful for you to brush up your tensor calculus, because let's ignore the spelling, let me just correct it anyways, calculus. So we'll be dealing with a lot of mathematical expressions that would involve all these tensors and these indexes, mu, nu, and so on, right? And it will be very mathematically dense calculation. So the idea is in the next video we'll be talking about conformal generators, where we'll be discussing different type of conformal symmetries, translation, dilation, and so on, right? Special conformal transformations as well. From that we'll then proceed on developing the conformal algebra, which is really just the commutators of these different transformations, right? And those commutators will give you a conformal algebra, and then we can proceed further with multiple topics of conformal field theory.